Hi everyone, I'm Tao from EPFL Switzerland. So today I'm going to present Monarch. It's the first fuzzing framework for finding memory and semantic bugs in distributed file system. This is a job work from EPFL and the University of Waterloo. Distributed file systems are the backbone of model computing infrastructures. They have been widely adopted in high-performance computing, serverless, and machine learning model training. However, they are not as reliable as what we expect from a critical infrastructure. For example, Ceph and Lustre have over 10,000 reported bugs over the years individually. There are several reasons make distributed file systems such fragile. First, most distributed file systems are written in memory-unsafe languages such as C and C++. So they are susceptible to memory bugs. Second, the nature of distributed systems adds another level of complexity. This complexity makes distributed file systems more susceptible to memory and semantic bugs. For example, multiple clients highly concurrently access the file data saved on servers, and servers have to duplicate the data on multiple nodes to torrent failures. In this case, it's important to find and fix bugs in distributed file systems to avoid security attacks and avoid data loss or data corruptions. There are existing approaches to fight bugs in distributed systems, which is also applicable to distributed file systems. However, all these techniques are not automatic or scalable. For example, regression testing requires users to manually write test cases, which often missing corner cases and thus missing a lot of bugs. While model checking always faces the state exploring problem, even various reduction techniques are applied. Similar to regression testing, formal verification always have the need to apply a lot of manual effort to write proofs. And thus, usually it's only applied to the critical components of distributed systems like verify the consensus protocol raft or Paxos. So in this case, we may wonder, are there any automatic and scalable bug fighting techniques for distributed file system? The answer is fuzzing. So fuzzing has become a practical and impactful approach for fighting bugs because of its automatic state exploration and scalability to large programs. For example, the Linux kernel fuzzer syscaller, which is also a file system fuzzer, it detects over 1,000 bugs every year since its release. Specifically, more than 800 bugs have been detected in local file systems. These local file systems are the subsystems of Linux kernel. However, all these existing file system fuzzers are designed specifically for local file systems. So let's take a look at their workflow to see if we can directly apply local file system fuzzers to distributed file system. So generally, the single node and in-kernel local file system runs inside a virtual machine or a library OS. And then there's a generator or mutator produce test cases, which includes a set of syscalls. And the test cases are passed to the local file system for execution. During the execution, checkers are applied to asserting different kinds of bugs. In the same time, the runtime information like coverage are collected and returned to the mutator as a feedback to improve the mutation efficiency. So it looks quite straightforward to directly apply local file system fuzzers to distributed file systems. However, if we think deeper, actually such an approach is inadequate. So firstly, local file system fuzzers are limited to testing single node and in-kernel file system. However, distributed file systems consist of multiple components that runs across multiple nodes and across kernel user space. This makes local file system fuzzers applicable to distributed file systems. In this case, we need a multiple node and cross-kernel user space fuzzy architecture for distributed file systems. And second, local file system fuzzers testing the targets with syscalls only. However, distributed file systems are designed to take in concurrent syscalls and to tolerate distributed faults like network partition or node crashes. So to effectively testing a distributed system, we have to also include distributed faults as a testing input space. Moreover, as local file system fuzzers are designed to test in single node and in kernel file system, it can only collect the single kernel execution states as the feedback. However, as we mentioned, distributed file system has multiple components that runs across multiple nodes and across kernel user space. So we have to come up with another representation to better represent the cross-node and cross-context execution states. Finally, existing file system checkers can only report memory bugs and one kind of semantic bug, crash consistency bugs, under the sequential testing scenario. However, semantic bugs in distributed file systems are more than crash consistency bugs, and these semantic bugs can be exposed under different testing scenarios, like testing under concurrency and testing under distributed faults. So in this case, we also have to come up with a new systematic semantic checker for distributed file systems. So to complete the aforementioned missing pieces when you apply in local file system fuzzers to distributed file systems, we propose Monarch. It's the first distributed file system fuzzer. So Monarch follows the controller and workers design model. There's a set of workers, and each worker is one fuzzy instance which runs a distributed file system instance. So the controller centrally controls multiple workers for parallel fuzzy. To be able to test diverse distributed file system architecture like in kernel or user space file systems and isolate the controller from the testing file systems, each worker set up a distributed file system instance inside multiple virtual machines instead of directly in host or in containers. And for each virtual machine is one distributed node. Inside the nodes, there's a file system server or file system client, and there's an executor which communicates with the controller and also executing the test case. In the controller side, there are three components. Firstly, there's a mutator, which produces test cases including syscall sequence and the injected faults. And it will distribute the test cases to different workers and different nodes. And then there's a component that collects the different execution states from executors and then aggregates them as feedback for the mutator. Finally, there's a checker. It also collects the per node execution states to ascertain if there's a memory bug or if there's a semantic bug. So due to the time limit today, we will only introduce the mutator and the checker. For other components, feel free to check our paper. As we mentioned, we are testing distributed file system from the most critical input space, the syscalls and the distributed faults. Then there could be three testing mode combination, like you can test in the file system with syscalls only, testing with distributed faults only, or you can test with syscalls and the distributed faults together. As it's meaningless to testing with pure distributed file system, distributed faults, so we only decide to test the distributed file system with only two modes. We name the two mode as non-fault mode and fault mode. So in the non-fault mode, we test the file system with syscalls only. This is quite similar to testing local file systems. And the syscalls are generated using the traditional syscall templates and mutation rules. On the other side, in the Feng mode, we testing the file system with 6 cores plus injected faults. And we focus on the most critical distributed faults like network partition or node crashes. So furthermore, when we consider injecting faults to the distributed systems, there are 3 questions we have to answer. First is, Monarch has to deterministically inject faults to the system because it has to mutate the test case further, and it has to be able to reproduce the bug once there's bug found. To realize this, Monarch adds synchronization primitives among nodes to accurately control the syscall execution and fault injection. Also, as faults can happen at any time during the test case execution. So that means there can have different fault injection granularities. Like in the final grade, you can inject faults in the package level. In the course grade, you can inject faults in the, at the syscall level or even the test case level. To balance the fault injection search space overhead and the granularity, we finally decides to inject faults at the syscall granularity. This means like a syscall is executed either inside a distributed faults or outside of distributed faults, but not partially. Last, we have to also consider when to inject faults. As Monarch is a fuzzing framework, it follows the revolution process of fuzzing. This is the core principle of fuzzing. It only inject faults after a test case triggers new execution states. Okay, next let's take a look at the checker. Monarch focused on 2 types of bugs in distributed file system, and they are the most critical bug types. That's memory bugs and semantic bugs. As it's quite straightforward to apply existing memory sanitizers like address sanitizer to distributed file system for finding memory bugs. So we will just skip it today and only focus on the semantic bug part. Now you may wonder what are semantic bugs in distributed file system. If we abstract the distributed file system as a state machine, then the state transit among each other with the execution of syscalls and the distributed faults, right? And how the transit should behave are the distributed file system semantics, which is specified in the specification like POSIX specification. And then, once the file implementation violates the specified semantic, that means there's a semantic bug. And the semantic bug happens into different scenarios, like sequential execution, concurrent execution, or even syscall execution under the distributed faults. Unfortunately, existing semantic checking can only find the one kind of semantic bug, like the crash consistency bug under the sequential execution. It will miss all other kinds of bugs and in other scenarios. So to be able to detect all kinds of semantic bugs in all scenarios, we propose the semantic checker, SIMSC. Let's take a look at the workflow of SIMSC. Given an input, which includes syscalls and distributed faults, we firstly execute it on the file system instance to know the runtime states beta. And then SIMSC takes the same input and some other runtime information like the execution time steps to emulate the syscall and fault execution to derive a set of oracle states sigma. And then we compare if beta is belonging to sigma. If it's not, then there's a semantic bug. So this is a workflow of SIMSC. Following this workflow is quite straightforward to understand, like, it's quite straightforward to emulate the semantics under sequential execution. You just need to emulate the syscalls one by one according to the specification, right? For example, if you have a test case with 2 syscalls, like you make a file and then you set the attributes on it, you only need to emulate like the directory entry and also the extended attributes, and then you can know the oracle states, right? But it's quite challenging to emulate the states under concurrency and distributed faults because the specification doesn't tell you how the semantic is. For example, if we have a test case including this full syscalls and maybe some other syscalls proceeding, then in this case, from a user perspective, we only know the execution time steps, like when the syscall starts and when the syscall finish, right? You don't know any other informations. And then how could you know the execution result, right? Because their execution are overlapping. Then in this case, also, like how could we emulate the semantics? So our checker solves this problem by split syscalls into atomic operations. Like, for example, we have the A key write, right? We split it into two for key write because in the targeted file system, the write is atomic in the for key granularity. And then, like for file treatment model, actually we didn't split it because itself is already atomic in the semantic level. Next, we will serialize all concurrent operations into sequences and then emulate the semantic on each sequence. That means for one concurrent execution, you can have a lot of, you can have different sequences and then different oracle states. As long as the runtime states matches to one of the oracle states, then it's correct. Otherwise, it's a semantic bug. For example, here, actually, we can have multiple sequences, like you can have two for key write followed by file change mode and then a for key write. And then like a for key write followed by file change mode and two for key write, right? And some other sequences. So let me show you a real bug we found in Ceph to further understand this procedure. Assume we have a concurrent test case which including two syscall sequence, and after running this test case in a Ceph instance, we know their runtime step, we know their execution timestamp, and then we know their execution order and their overlapping information. So given this information, let's see how we emulate the states. Because the syscalls here are already atomic syscall operations, so we don't have to split them. For the first two opens, because they are concurrent, they were concurrently executed, so there could be two orders between them, right? So also there could be two possible execution results regarding to the file mode. It can be X or Y. And then the change mode was executed without any concurrent syscalls, so the result is deterministic, which should be Y. Finally, there's two stats were executed concurrently, so there should also be two orders between these two syscalls. However, because these two syscalls are read syscalls, so they don't affect each other, so we will only explore one order between them and then prove another order to improve the emulation performance. So according to the emulation, we know like the file mode, the two stats should retrieve Y as the file mode. However, in the runtime, the client to actually retrieve X as the file mode. So that means it's a semantic bug. So actually this bug is because there's the incorrect concurrency control in the Ceph server, which led to this bug. Now we can find semantic bugs under sequential and concurrent executions when there's no fault. Because once there is fault, the file system, the syscall semantics get changed. For example, if you execute a write on the fault, can you directly apply the original semantics to get the execution result? Obviously, we can't, right? Because once there are some faults, maybe the file system just becomes unavailable, and thus the write can still fail, even if the parameters are valid. So to solve this problem, our checker will first check if the file system is available to this syscall. If it is, then it just apply the original semantic. Otherwise, it will just return error during the emulation. So the availability is emulated from the availability model we manually extracted from the distributed file system, which requires minimal manual effort. So now we have built this fuzzing framework. Let's test it to see if it's really effective. If it's really effective. So we run the Monarch on 6 popular distributed file systems, and finally we found 48 bugs across all the file systems, including 40 memory bugs and 8 semantic bugs. Further, we analyzed the characteristics of distributed file systems, and we found fuzz play a critical role in exposing these bugs. For example, 14 out of 40 memory bugs and 3 out of 8 semantic bugs exposed on the fuzz. So this shows the significance of testing both syscalls and distributed fuzz together. And also we found vulnerable code are scattered in both servers and clients. Interestingly, the root cause of semantic bugs are mostly in server side. We also found that the bug explorers depends on specific distributed file system configurations, like there's a cluster file system bug. It can only be exposed when the instance is configured with exactly 2 servers and in a distributed mode. So in conclusion, to test distributed file systems in an automatic and scalable fashion, we propose Monarch is a push-button fuzzing framework for distributed file systems, including a set of building blocks like multiple node and cross-context fuzzing architecture, and a 2-step mutator for testing file systems with syscalls and distributed fuzz. And also we have a semantic checker for distributed file systems for finding all kinds of semantic bugs. So from the evaluation, we can see fuzzing is still as effective in distributed systems as it is in local systems. Our artifact is available on GitHub. Please feel free to try it. And thank you. I'm happy to take your questions right now.